A black hole acts as the ultimate stress test for our understanding of physics. It is the environment where the smooth, continuous geometry of general relativity collides with the discrete, probabilistic rules of quantum mechanics. When applied to this environment, our best mathematical models generate paradoxes at three distinct locations: the event horizon, the stretched horizon, and the central singularity. To understand black holes, we have to analyze these specific boundary points to determine exactly where our mathematical logic diverges from physical consistency. A common assertion is that once you cross an event horizon, space and time swap roles. Your trajectory through space becomes as strictly unidirectional as your passage through time. That interpretation relies on classical gravity. Albert Einstein finalized general relativity. Physicists have struggled to reconcile the infinitely dense mathematical points it predicts with the finite reality demanded by quantum theory. Decades later, Stephen Hawking applied semi-classical field equations to the event horizon, proving that black holes emit thermal radiation. This calculation eventually produced the firewall paradox, a direct conflict between the rules of thermodynamics and the geometry of gravity. Many of these presumed physical realities, time swapping with space, walls of fire, and infinite densities, are actually fictitious mirages. They are artifacts generated by pushing mathematical models past their valid parameters. The idea that space and time swap roles comes from the standard coordinate system used to map black holes, known as Schwarzschild coordinates. These coordinates locate a point using a time measure, t, and a radial distance, r. This animated plot displays the mathematical components of the Schwarzschild metric. Notice the specific term, 1 minus 2m over r. When the radius r dips below the event horizon, that term becomes negative. On the graph, you can see the radial and time coefficients crossing the zero line and inverting signs. Mathematically, the signs flip. Physically, your clock does not become a ruler. This is a coordinate singularity. The math breaks down because of the grid we placed over the space, not because the space itself is broken. If we want an unbroken map of the entire black hole, we use Kruskal-Sakaris coordinates. This global framework completely eliminates the sign flip at the event horizon. Looking at this Kruskal-Sakaris diagram, we can trace the paths of light signals as 45-degree lines. As those lines cross the hyperbolic lines representing the event horizon, they remain perfectly straight. No spatial dimensions swap. But mapping the space this way introduces a new mathematical consequence. The Kruskal equations smoothly map outward, predicting a region where time runs in reverse, a white hole, and a tunnel connecting two universes, known as an Einstein-Rosen bridge, or wormhole. A white hole functions identically to a black hole, except it only ejects matter. The equations allow this, but the physical universe does not. A system that only decreases in entropy directly violates the second law of thermodynamics. Furthermore, the mathematics show the wormhole is highly dynamic. The tremendous gravitational forces cause the throat of the tunnel to stretch and snap shut far faster than a light signal could ever cross it. We can derive white holes and wormholes flawlessly on paper. Because those objects cannot exist in reality, we have a clear proof that mathematical validity is entirely separate from physical reality. To find where the math breaks down next, we move a Planck length outside the event horizon to a boundary known as the stretched horizon. This hot membrane is the proposed source of Hawking radiation. Physics accepts a standard postulate. Outside a massive black hole, the environment can be accurately described by semi-classical field equations. These equations predict that any observer hovering statically outside the horizon will experience a flux of thermal radiation. In this diagram, observer A is a fiducial observer, or FIDO. By hovering just above the event horizon, FIDO sits in an intense field of Hawking radiation. In panel B, we drop a free-falling observer, or FRIFO, from the exact same position. According to the clock postulate, observers at the exact same position with zero relative velocity do not experience gravitational redshift relative to one another. At the moment of release, both the hovering FIDO and the falling FRIFO must observe the identical, intense frequency of radiation. Comparing these effects, in empty space, an accelerating observer experiences the Unruh effect, a static thermal bath, but Hawking radiation exerts a net outward energy flux, generating real radiation pressure. This pressure interacts with the free-falling observer, physically pushing them off their geodesic path. Deviation from a geodesic is an observer-independent reality. If the hovering observer sees the falling observer battered by radiation pressure, the falling observer must physically feel that intense acceleration. They literally experience a solid wall of high-frequency fire. If the falling observer burns up at the horizon, it violates one of the most foundational rules of general relativity, the equivalence principle, which states that a free-falling observer should experience no drama, feeling exactly as if they were floating in empty space. The math of semi-classical field equations guarantees Hawking radiation. That radiation guarantees an outward energy flux, which mathematically guarantees a firewall. Yet the existence of that firewall breaks the very principle Einstein used to build the theory of gravity. Past the event horizon lies the final mathematical breakdown, the central core. Traditionally, this is modeled as a singularity, a point of infinite density and gravity. In 1965, Sir Roger Penrose proved that if an event horizon forms, general relativity makes a singularity an inevitable mathematical outcome, earning him the Nobel Prize. Penrose built his theorem analyzing null geodesics, the paths of light. To track a photon, physicists use a mathematical tool called an affine parameter. Recently, astrophysicist Roy Kerr published a direct challenge to this model. As shown in this diagram, null geodesics, the paths of light, converge and terminate, but the time-like geodesics, the paths of matter, are projected to continue. Kerr argues that an affine parameter terminating simply means we can no longer track the light path using that specific mathematical tool. The equation ends. It does not mean the physical fabric of space and time crushes itself into an infinitely dense point. Kerr's own solutions for rotating black holes support this. In a Kerr metric, a math allows time-like geodesics to pass through the interior indefinitely, suggesting matter can survive and orbit inside the black hole without ever hitting a central point. Just like the space and time swap at the horizon, the singularity at the core is likely a mirage. We have interpreted the boundary of our mathematical parameters as the physical boundary of the universe. When we test our equations against the extreme gravity of a black hole, the models fracture. The space-time swap is an artifact of the Schwarzschild map. The firewall is a contradiction between semi-classical radiation and the equivalence principle, and the infinite singularity is a misinterpretation of geodesic geometry. Theoretical physics currently faces the information paradox, a massive debate over whether black holes destroy the quantum data of the matter they consume. To solve it, we have to determine exactly which parts of our equations represent physical reality and which are just math. Mathematical rigor is required to understand gravity, but we must rigorously separate the physical consequences from the fictitious mirages generated by the coordinate systems we choose. The next major breakthrough in formulating a unified theory of quantum gravity will require identifying exactly where our current formalisms break down. In the most extreme environments in the universe, our maps of reality are ultimately more fragile than the reality itself.